Hey all, welcome to ShareTrek. This is Raj here. First of all, a very big thanks to all our subscribers, members, and Patreons for keeping me motivated to continue bringing you HIV videos. And without your support, it wouldn't have been possible, especially to the Patreons and the members. And today I'm going to do something different. Usually, I talk to you about a therapy that's in clinical trial, how it works, or a therapy that's already available in the market, and I describe the mechanics of how it works. But one of the other aspects of HIV is that people who suffer from HIV would like to get assurance that it's going to be cured and it's going to get cured soon, and some logical and rational basis for making that kind of a statement. And that's exactly what I want to present to you today. And with that said, let's get started. Welcome back, friends. Today's topic will either get you saying, Raj, this is great, thank you, or you'd say, I don't want to be the scientist, just tell me when the cure comes. So I hope you are the former who says that this is great, Raj, thank you. With that in mind, I'm going to proceed. I'm going to very briefly explain the gene editing technology progress of what is currently in use, and then show you a plethora of Cas nucleases in test that might come into use in the future. Then we'll also look at Arbor, which is a company that I've been very excited about, and it has got a whole lot of nucleases that it has discovered, and it has got a platform of its own, which is going to have great potential going forward. Now, I understand that you're a layperson, you're not a genomic investors. Our genomic investors understand all the points that I mentioned so far. So I'm going to break it down for you. Nucleases are a special molecule which are able to cut DNA. They could do a single strand cut or a double strand cut. It depends on the nuclease. Nucleases are of various sizes. The biggest and most famous example of nuclease is CRISPR-Cas9, where Cas9 is a nuclease. And it became famous because of the Nobel Prize that was awarded to Jennifer Doudna and Emmanuel Charpentier. And we also have Feng Zhang, whose name should always be mentioned when we talk about CRISPR-Cas9. He's a visionary. I think he has not got his due. He's not got as much recognition as he should have, in my opinion, of course, because he has pioneered not only CRISPR-Cas9, but he has gone into various other gene editing technologies, and he has created a lot of companies. One of them is Arbor, another was Beam, and these companies take the gene editing technology a step further and make it even more precise, even more accurate, even more specialist for a particular application. So if you were to think of HIV as a defect which has to be repaired, just imagine when you get a handyman to come to your place to do some repairs. So he has got a toolkit. So there are screwdrivers, there's a drill machine which can take screwdrivers of various kinds, plus, minus, different sizes. It can also take drill bits, and the same machine becomes a driller, and the same machine becomes a screwdriver. So that's a versatile tool. And then he would have other tools to do precision cuts here and there. And then he uses all those tools to do the repair in your house. And then he goes away. If he didn't have those tools, the same repair would have taken a long, long, long time. Okay. So in our early days of medicine, the scientists and doctors were watching people who had diseases, and they would study the symptoms of the disease. And they would say, if these symptoms are all present in an individual, then the disease is such and such. And then they will start treating those symptoms by giving medicine for each of those symptoms. So discovering medicine was based on symptoms, and a collection of medicines was given to address a collection of symptoms of a particular disease, so that the symptom could be managed until the disease goes through its term and leaves the body. So that's how it was done. And then there were some diseases which would never leave the body, like cancer, and Alzheimer's and Parkinson's, those kind of diseases. Those became the dreaded diseases for which we did not have a cure. At the most, what we could do was give palliative care, and that's how it used to be. Then, a long time ago, we had the first discovery, that was the discovery of DNA. And then we started understanding that life has a blueprint, and the blueprint is the DNA, and the DNA is a strand. It's a double strand ribbon, and each of the points in those strands stand for a particular protein, and each of those protein has a particular function in the body, and as a result of which the DNA describes the entire organism, right from gestation to birth to growth to digestion to reproduction and eventually to death. The whole cycle is defined in the DNA. And then we started learning about stem cells, which then mature into different cells for the body. So the knowledge started growing. And somewhere along the line, the earliest of DNA editing started. It was the zinc finger nuclease, or ZFN. And then we had talons, which was another technology. These technologies were cumbersome and they were difficult to set up, but they managed to do gene editing, and it was the early days. And then we had CRISPR-Cas9 come in. So friends, I'm going to show you a chart and I'm going to walk you through it. It shows the progress of technology since ZFN and talons. This is my very first slide for you, where I'm going to show you the sequence of this invention. 1994, we had the discovery of the ability to edit DNA, and zinc finger nucleases, or ZFNs, were the first editing system that was discovered in 1994. And then we had talons, which is transcription activator like effector nucleases. It was discovered in 2009. And then we have CRISPR-Cas9, which was discovered in 2012. And then we had CRISPR-Cas12a, which was discovered in 2015. And we have base editing 2016, prime editing 2019. Now these are all already being used in the industry to create various gene therapies and new medicines. This is my next table, in which you will find some repetitions. CRISPR, base, prime editing. These are already something I spoke to you in the previous slide. So CRISPR makes double-stranded cuts. And the reason why CRISPR became popular was because talons and ZFN were difficult to set up, and it took a longer time and it was more expensive. And CRISPR became a more inexpensive way of getting into it. However, when you want to license a product which you have created using CRISPR-Cas9, you have to pay a license fee. And the only problem that scientists found with CRISPR-Cas9 was that double-stranded cuts would mean that DNA would make automatic repair, and those repairs may not necessarily be perfect every time. There could be errors, and those errors could cause problems. And also double-stranded breaks in different places could become carcinogenic, so they created a map of the DNA where you can't use CRISPR-Cas9. But still, CRISPR-Cas9 was used to deliver successful therapy for sickle cell disease and beta thalassemia. And what is more, it was not just one company that did it. Multiple companies have come up with genetic medicine to cure sickle cell disease. It's a once and done cure. So you have CRISPR Therapeutics with their Casgevy, and you have got Bluebird Bio with their Zynteglo therapy for beta thalassemia, and they have two more therapies. And we now have Beam Therapeutics working on Genicell, and Bluebird's LifeGenia. That name was not coming to me, LifeGenia. And when you look at Bluebird Bio as well as CRISPR Therapeutics and Beam, you can see that the same disease can be cured using different strategy, and all of them involve manipulating one gene or the other. And that gives us an idea of how versatile gene editing can be, and that gives the scientists an opportunity to cure the same disease using various different methods and altering different genes in order to get the same result of getting the patient rid of the syndrome or the disease that they are suffering. So CRISPR-Cas9 has already proved that it is market worthy and it is ready for the heavy duty work. But considering the fact that double-stranded breaks cause problems, we have base editing. Again, Feng Zhang has got his hands on this, and he's a prolific discoverer, a great scientist. Now, base editing uses Cas9 nickase, which is a modified Cas9, and Cas9 is present in various bacterium, and it depends on where you extract the Cas9 from, that the size of the Cas9 and its properties. So Cas9 nickase helps to do editing of a single base in the DNA. And that way it reduces the risk of double-stranded breaks, and there is no off-target editing. But there is a problem, because in the base editing, it has to go along with a particular nuclease, which is going to change a particular nucleotide into another. So if there are two nucleotides adjacent to each other which are of the same type, like if there are two A's next to each other, and if the base editor was supposed to convert an A into a different alphabet, and there could be off base edit out there, in that remote case there will be a bystander effect, as they call it. So that's the only problem. But base editing can be used in many places where it's a single edit that is needed in the DNA to cure a particular syndrome. And then we have prime editing, which is like the best example to describe that is like a digital word processing. You tell it what to find and what to replace it with. That's what prime editing does. And it does precise insertion of DNA sequences, and it's able to target multiple mutations with a single guide. And it's got a engineered Cas9 protein fused to reverse transcriptase enzyme to perform all this work. And it would be able to help cure diseases such as cystic fibrosis, which is caused due to a bunch of mutations happening in a particular point on the DNA. And then we have other approaches. One is called epigenome editing. In epigenome editing, the gene expression is modified without altering the DNA sequence. So it's more or less like the volume control. So those of you who have seen old stereo systems, you had the volume, you had the balance, and then you had treble and you had bass. So you don't need to increase the volume. You leave the volume where it is. You could change the balance to move the audio to the left channel or to the right channel. You could keep the balance in the center, so both channels have got equal volume. And then you could manipulate the treble. You can reduce the treble to remove the sharp frequencies. You can boost the bass or the bass to improve the soft frequencies. So you could manipulate them to get a different quality of sound without increasing the volume. So epigenome editing is something like that, where the DNA sequence is not altered, but the potency of particular parts of the gene is tuned down or tuned up in order to cure a particular syndrome or a condition that is caused due to faulty calibration of the DNA sequence. So the calibration is adjusted, it's not edited, just the calibration is adjusted so that various components of that DNA sequence perform in the appropriate proportions. So that's epigenome editing. And then we have the exciting Cas-Mini, which is a very small alternative to Cas9 enzyme, aiming to improve delivery and reduce toxicity. And it has been engineered out of Cas14, and there are clinical trials going on in it. So these are all the things that are happening. And those that are not scientists and those that are not following genomics would ask me, Raj, what is all these things, Cas and all that you're saying, nuclease and edit and all that stuff, how does that matter to me? I'm looking for a cure for HIV. Well, so when you look at AGT103-T, I suspect they use talents out there to do the modification, but basically they're going into the CD4 T cell and making modifications in order to remove the CCR5 expression. So they are dialing down the CCR5 expression so that the CD4 T cell doesn't produce CCR5. So that's a genetic manipulation. If you look at EBT101, they have got two guide nucleases, which are two guide RNAs, which are going to attach to two different spots on the host genome where HIV is found. And that part of the DNA on host genome is going to be the HIV, which is embedded provirus, which is embedded into the host genome. And then it's going to make two precise cuts and take out the GAG gene. If the GAG gene is gone from the HIV sequence, then HIV cannot replicate itself. It will be defective. It will never be able to infect anybody else. Now, to do those, they are using CRISPR-Cas9. Now, the same thing can be done in different ways. For example, if I was to, I'll give you an everyday example. If you want to make a cup of tea, different people make a cup of tea in different ways. Some people do it the traditional way. They could put the kettle, heat the water, and then they could add tea leaves into it and then pour it out, put milk, and so on and so forth. Yet there are others who would have just heat a kettle of water. They'll have a cup in which they have a tea bag, and they pour the hot water into it, wait for it to sleep, and then they put milk and then they drink. So there is more than one way to do a thing. So when you're looking at genes, you're looking at a series of codes which are there, which are interacting with each other. So once a particular sequence is verified, then they identify what is the property, how does that sequence manifest in the body. So that way they can identify the genes which are responsible for creating enzymes which break down certain proteins and so on. So this kind of a knowledge helps the scientists to understand how various genetic diseases happen and how various viruses take advantage of the services available in our DNA in order to propagate and in order to go and create problems in our body. HIV is one such virus which is getting into human body, and it's implanting itself into the CD4 T cell in the human genome and then replicating from there and infecting more CD4 T cells and taking over the entire immune system and causing AIDS. We know that already. We know the structure of the HIV virus, and we know the RNA inside it. So right now it's very difficult to visualize a gene editing system which can be released into the body, which will find HIV virus wherever it is, go inside the capsid and cut off the RNA and finish HIV. That's not possible at this point of time. Maybe some brilliant scientist might come up with an idea to do that. But what is possible right now is that we have a very good understanding of the entire life cycle of HIV, how it propagates and multiplies and how it enters the cells and so on and so forth. So gene editing can be used in order to create futuristic therapies that will be able to disrupt each stage of the HIV replication by depriving HIV of the protein or enzyme or transcriptase or anything that it needs in order to build its capsid, in order to build its GP120 or GP41 or any component. So as you deprive components for HIV, then HIV will have to continue mutating so that it can still be viable without those components. And when that happens, we'll be coming up with more gene therapies to attack the remaining components until we have dispensed off with HIV altogether and HIV is unable to infect anymore. Now let me show you what is the hope for the future. So right now I'm looking at this spreadsheet. This is the list of all new nucleases that are being studied. You have Cas14a, 1a, and so on. There's a whole lot of them. And some of them are very, very small. Right now, the problem with CRISPR-Cas9 is the size is huge, and fitting it into a adeno-associated virus to deploy into the body is becoming difficult. So there are smaller Cas molecules that have been found, and they have some specific qualities. And these things can be harnessed, and we can then create the toolbox that your handyman comes with to repair anything in your house. So we'll have an entire toolbox of drill bits, of screwdriver heads, of chisels, of hammers, of saws, you name it. So all the equivalents of that for manipulating the genes and for editing the genes would be possible as we study more of these. These are all being studied right now. They have the capability to edit genes in a specific way. And once these are all tested out and we understand all their qualities, then it can go into non-human primates to study how it works inside a living organism. In Petri dish, anything can be done, but in a living organism, it's a dynamic system. So once it works in non-human primates, then it can be tested in human volunteers. And once the editing method is perfected, then it can be deployed into creating therapies. So what it means is that in the future, we are not only going to have CRISPR-Cas9, base editing, TALENs, ZFN, prime editing, and minicas. We are going to have a whole lot of other Cas proteins which have got very, very specific properties. So now scientists can look at the entire life cycle of HIV and they can pinpoint the target that they want to hit to disrupt HIV. And in order to hit that target, they will have appropriate gene editing tools available so that in the location where those HIV life stage transitions happen, they can identify what are the enzymes, what are the nucleotides, what are the components of the cell HIV uses in order to build that component. They can create gene editing interventions to go into the cell and block the creation of those enzymes, those components, so that HIV doesn't get the necessary tools for it to build its capsid, to build its RNA, to assemble it together and deploy it out of the cell to infect other CD4 T cells. So friends, that's the exciting future that I'm talking about. And over and above that, today in our channel, we had a live stream of NVIDIA and their AI system. And NVIDIA has worked extensively to map proteins, and it's also working with the AI system called BioNemo. And it has got excellent promise for the future. So it's going to enable scientists and researchers to try out everything in the virtual world even before it goes into NHPs and into the preclinical trial. So there is a omniverse being created. Right now they have created omniverse factories in which they can create the robots training so that everything can be planned out in the virtual world. And once everything works perfectly and the robots, virtual robots in there work perfectly, then all of that can be translated into real world in the same scale and same size, and it will work perfectly. So there is an omniverse that will be created for the human body, and in that we can test out all kind of gene editing and everything, and the AI system will hasten the process of clinical trials, hasten the process of identifying candidates. So I think we are entering a very bright future, and CRISPR-Cas9 has kickstarted the whole thing, and right now humans are using their own natural intelligence, and increasingly they are starting to use artificial intelligence, and NVIDIA is providing even more powerful AI capabilities going forward, and that's going to help the scientists to crack the problem of HIV once and for all. I hope you guys are motivated by this, and I would urge that you go to the ShareTrek Genomics channel, the original channel, and I have the live stream. Go to the live stream section and check out the NVIDIA live stream. It doesn't have everything for genomics. It has got everything, but a part of it is genomics. So you watch the whole thing, you'll understand the promise of AI and the promise of gene editing together to solve HIV issue. So with that, my friends, I'd like to finish this video here. Stay hopeful, stay happy, and stay motivated. Have a great day. Bye for now. I'll catch up with you in the next video.